Hello all and welcome to the Basics.Academy channel. In this video, we are going to solve the problem deleting the middle node of a linked list. Let us get started with it. First, what is a problem? You are given the head of a linked list, delete the middle node and return the head of the modified linked list. The middle node of a linked list of size n is the n by 2th node from the start using zero-based indexing, where floor of x denotes the largest integer less than or equal to x. For example, this is a given linked list having 7 nodes. Let us trace the explanation how the middle node is being deleted from the given linked list. The above figure represents the given linked list. The indices of the nodes are written below. These are the indices 0, 1, 2, 3, 4 and so on. Since n is equal to 7, node 3 with value 7 is the middle node, which is marked in red. We return the new list after removing this node. We have to remove this node and then return the list containing only 1, 3, 4, 1, 2, 6. What exactly is happening? As soon as you reach the previous node or the node previous to the middle node, then the next pointer of this node should point to the next pointer of the middle node. Let me iterate that again. As soon as we reach the node previous to the middle node, in this case, which is 4, we have to remove this link. That is, we have to point the next node of 4 to the next node of the middle node. The first question is, how are we going to ensure that we are at a node which is previous to the middle node? This is the first question. Given the linked list, first we have to identify the middle node minus one node. Once we are at a node which is just before the middle node, only then we can start about the linking. One approach is you traverse the entire linked list once, calculate the value of n, then calculate the value of n by 2, then again traverse the list and go up till middle node minus one node. Once you reach the middle node minus one node, then you go about with the linking. However, in this solution, we are doing two passes. Just think about it. Can we do it in a single pass? The answer is yes, we can do it in a single pass by making use of two pointers. We can do it in a single pass by making use of two pointers. Let us look at that solution of using two pointers and accomplishing the solution. So here we are. What we are going to do is, we are going to use the approach of slow pointer and fast pointer for traversing the list. The advantage of using slow pointer and fast pointer is, slow pointer will move one node at a time and fast pointer will move two nodes at a time. The slow pointer starts from the first node and the fast pointer starts from the second node. The fast starts one ahead, it moves 2 times, whereas the slow lands on middle minus 1 when fast hits the tail. That is, when the fast node reaches the end of the linked list, the slow node is on the middle minus 1 node. That is what we want. When the fast reaches here, that time the slow pointer is at middle node minus 1 node. Thus, we rewire the linking over there. That is, slow.next is equal to slow.next.next. Essentially, removing the link between slow.next and the middle node. Let us see the code of doing this. What we do, we initialize the head to the slow pointer and the fast to the head.next pointer, making sure that slow starts from the first node and head starts from the second node. Then as long as fast.next exists and fast.next.next exists, that is, as long as we are starting fast from here, as long as fast.next exists and fast.next.next exists, then you go inside the loop, you move slow pointer one at a time, and you move fast pointer 2 nodes at a time. That is, slow is equal to slow.next. So slow is equal to slow.next. Slow comes here, and fast is equal to fast.next.next. Right? So fast comes from 3 to 7. After first iteration, slow is here and fast is here. Let us look at the while loop condition, which again says while fast.next it is true and fast.next.next, that is also true. Again we come inside the loop and we move slow by one node. So slow is now at 4 and fast is now at fast.next.next, right? So slow is at 4 and fast is at 2. Okay. Now we check fast.next. It exists, but fast.next.next is null. So the while loop will not execute. Make a note here. Slow is at node 4, right? And fast essentially has reached the end of the list. That is what we wanted. Slow is pointing at middle node minus 1 and fast has essentially reached the end of the linked list. So what we do the rewiring. We do the rewiring, we remove this link and connect 4 directly to the node after the middle node. How we do that? This is the next pointer of the middle node minus 1. So we do slow.next, right? Slow.next is equal to slow.next.next. Essentially removing the middle node. This is how we rewire the list connection to drop the middle node. That is slow.next is equal to slow.next.next. And at last we return the head of the linked list. This is the ideal approach of deleting the middle node of a linked list, wherein you use 2 pointers. The slow pointer moves 1 node at a time. The fast pointer moves 2 nodes at a time. When the fast pointer reaches the end of the linked list, the slow pointer is pointing at middle node minus 1. As soon as we reach the middle node minus 1 node, then we rewire the connection. That is, we make sure that the middle node minus 1's next pointer is pointing to the middle node's dot next node. That is, slow.next is equal to slow.next.next. So this is slow. So this is slow and this is slow.next. Okay. So what we say, slow.next is equal to slow.next.next. Now slow.next.next is 1. Ideally, this becomes pointing to this node, essentially removing the middle node of the linked list. So this is how you remove the middle node of a linked list. The time complexity in this case is big O of n, since we are iterating the list once and the space complexity is big O of 1, as we are not using any variables to store the linked list. Hence, the space complexity is big O of 1. And at last, we return the head of the new list by deleting the middle node. I hope you would have learned something valuable today. If yes, please do like, share and subscribe. Thank you.